In the last two videos, we considered linear systems. So from this video onwards, I mean, in this video and the next one, we'll be looking at non-linear systems. So let's see what non-linear systems are about. Our goal here is to understand dynamics near equilibria in non-linear dynamical systems. We'll look at topics like linearization, Jacobian matrix, Hartman-Grobman theorem, hyperbolic fixed points, non-hyperbolic fixed points, and local invariant manifolds. Let's get ready for this. Now, the first point here, we're looking at, of course, generally speaking, we're looking at dynamic systems in this playlist altogether. Here we study systems of the form x dot equals f of x, where x is n-dimensional in nature. But then we can also look at it in two dimensions where we have x dot equals f of x comma y and y dot is equal to g of x comma y. And our goal is to understand behavior near equilibrium points. Now we've been doing that for linear systems. Now we go check the same thing for non-linear systems. Again, we've been talking about equilibria before now. So for equilibria, we talk about fixed points. A point x star is an equilibrium if f of x star is equal to 0. That is, if you have a function and you equate it to 0, the values you get are the equilibrium points for that this kind of f of x comma y. That is the right-hand side of x dot, the x dt, the y dt, like that. Same for g of x comma y. So in two dimensions, we have that f of x star comma y star is equal to 0, or g of x star comma y star is equal to 0. So at equilibria, the system does not evolve. So at equilibria, you have a kind of stationary, you have the system is in a stationary position at equilibria in a dynamical systems. So that it's what you call a steady state and all that. So imagine this example. Consider x dot equals x into 1 minus x. We've seen this logistic looking expression for, I mean, so many times. In fact, it has become a regular feature in almost every video under dynamical systems. So to find the equilibrium, you just equate to 0, right? And then you have x star equals 0, x star is equal to 1 based on what you have here. And then that takes us to the idea of linearization. Okay, so for linearization, near an equilibrium x star, we approximate f by its Taylor expansion, which is f of x, which is approximately f of x dot plus f prime of x star. You know, f prime is the same thing as d. D means the derivative of this multiplied by x minus x star because it is near the equilibrium point. That's why you have this whole x star thing going on. So, and since f of x star itself is 0, this expression will automatically disappear. And in that case, now we then have y dot equals ay, where y now is x minus x star, and a is the derivative of f of x star, or better still, the derivative of f of x evaluated at x star. And this idea is called linearization. Now, this may be looking like some abstract idea, but we'll go forward to look at to linearize. So the question is, why do we have to linearize? So for linear systems, y dot equals ay. Uh, so linear systems, y dot equals ay are completely understood. Their behavior is determined by eigenvalues of a. We've seen that a lot for linear systems, right? So though we are talking about non-linear system, but we're talking about linearization. So that now the deal here is you have a non-linear system, but you linearize to approximate some behavior so that you can get from them. So, and one key way we linearize is by using the Jacobian matrix. So for x I dot, which is equal to f of I into x1 up to xn. That is for systems like that. Maybe you have x dot equals f of something something, y dot equals something something, z dot equals something something, and all that. So this is like a generalization of that kind of idea with as many variables as possible and with as many as equations as possible. So the Jacobian is basically this. You have the f1, the xi, then you have the f2, the x2, the F3, the X3, all the way to the the F the Fn, the Xn, like that. Okay, so you have all of that going like that. So in two dimensions, since you are talking about if you're talking about two dimensions, you have j of xy, which is the so if you have variables f and x, you differentiate So in this case now, it means you have exactly this kind of setup. It means you have this kind of situation. So you have x dot is f into x comma y dot is g into x comma y. So if you have that kind of setup like that, so the Jacobian will be something like this. You have a matrix of, f for f sub x, that's partial f partial x, that's f differentiated with respect to x, f differentiated with respect to y, differentiated with respect to x, and g differentiated with respect to y. So that's the idea of Jacobian matrix, and it is a necessary process in linearizing. So imagine this system, you have x dot equals x minus y, and y dot equals x squared minus y. Of course, because of this x squared, this system is non-linear for sure. So what do you do? But the Jacobian thing to do, okay, yeah, you differentiate and you get one. Differentiate x with respect to x, you get one. Differentiate y with respect to minus y, you get. Differentiate minus y with respect to y, you get minus one. Differentiate x squared with respect to x, you get 2x. Differentiate y with respect to minus y, you get minus 1. Okay, to drive that home further, x dot is x minus y, right? So we have x dot to be x minus y, and y dot is equal to x squared minus y. So, and we're saying that we need the Jacobian of x comma y. So generally speaking, like what we've considered, this is going to be partial. Okay, of course, this is now f of x comma y, if you like, and this is g of x comma y. Okay, so for the Jacobian, for this part now, we have partial f, partial x. That is this expression differentiated with respect to x. Then we have partial f, partial y. So the same expression differentiated with respect to y. Then we also have partial g, partial x, then partial g, partial y. That's how the Jacobian goes. So j of x comma y now is equal to, so partial f, partial x. That means this x minus y differentiates with respect to x, you get 1. Then f differentiate with respect to minus differentiate the expression again with respect to with minus y. Of course, x is constant in that case. Minus y is what we're focusing on. So for that, we get minus 1. And then when you come down here, you want to differentiate this expression with respect to x. You can see y as a constant because x is the focus. So differentiate x squared with respect to x, you get 2x. Then come here now, differentiate this expression with respect to y. X squared is a constant in that case. Differentiate minus y with respect to y, and you get minus 1. And that's exactly what we have in this case like this. So the Jacobian is 1 minus 1, 2x minus 1. Okay? So we can also do that using SymPy, that's symbolic Python. So all you just need to do is you just say import SymPy as SP and then x comma y. So this is telling you that these are the variables you're using. X comma y is equal to SP symbols, that's SymPy symbols x, y, and then f, define f to be x minus 1, y, and g is x squared minus y. So you can get the Jacobian by just saying sympy dot matrix f of g, fg, this fg now, dot Jacobian in terms of x, y. And then in line 10, you declare the Jacobian itself, and then that runs and gives you the results. So you get exactly the same thing you have like that. Okay, so that comes out in a jiffy. I think it's becoming more than a jiffy. Okay, yeah. So you have this expression. So for uh, what if things get a bit more complicated and then you have another kind of expression? So all you just need to do is maybe we have, okay, let me even do maybe let me do 3 variables now. So we have FGH now. This is FGH, right? And I say that is equal to, so let me now say this one is okay. Let me say this is now say y raised to power 3 and then h. Okay, let this one suggest something to me. H is equal to, okay, yeah, let me do this. Yeah. So x cube minus y cube. And then I now want to have fg. So this will now have to be fgh in 3 variables. Now this will now be x, y. Aha. So I can even throw z into it. So plus z, okay, plus z. And then this is minus z raised to power 2. That's small z raised to power 2. And then this one will now be just minus z. Okay. So then we want to take the Jacobian of fg and h uh, with respect to variables x, y, z. So if I run this now, Okay, we have a problem here. Z. Oh yeah, I didn't define Z here. So X, Y, Z. Okay. Then symbols, I add Z to this, and then now everything should work fine. Yeah, that's that. So you see the Jacobian matrix of this system now, FGH will now be differentiate X with respect to X, you get this expression with respect to X, you get 1, Y minus 3Y squared, Z is 1. Then here you have 2X, this is minus 1, this is minus 2Z, this is 3X squared, this is minus 2Y, this is minus 1. So I mean this you can, even when you have more complicated systems, you can easily get the Jacobian like that. Okay, so with that in place, we can then have then we can go for linear stability analysis. So um linear stability analysis has this procedure. First of all, you find equilibrium X star by equating the F or G or H to 0, and then you compute the Jacobian. You compute the Jacobian, right? Evaluated at the X stars you got, and then based on that you find the eigenvalues, and then you can then classify the stability. So you talk about you based on what the eigenvalues may be. We have experience talking about stability in terms of eigenvalues. So, and then we go ahead to talk about eigenvalue classification in 2 dimensions, right? So, let lambda 1 and lambda 2 be eigenvalues. So we've done this several times, either under linear algebra or now I've been talking about dynamical systems. So, for eigenvalues, if both eigenvalues, lambda 1 and lambda 2, are 0, we have a stable node. So, then we say it's stable. If both are greater than 0, we have unstable node, that is unstable. If you have opposite signs, one is positive, one is negative, we have a saddle, and that means the system is unstable. Then if we have a complex number, so the real number of the complex number is less than 0, we have a spiral sink. That is a spiral system that is going to a particular point, and then in that case, the system is stable. If the real number part, if the real is greater than 0 for a complex eigenvalue, we have a spiral source. So that means a spiral that is growing out, that is unstable. Then if it is pure imaginary, just plus or minus something, we have a plus or minus something I. We have a center that's inconclusive. So you have I think that's what is called a limit cycle too. So if I may demonstrate all these things, I think I've done this demonstration amply. But let me just go ahead and do that again. So talking about stability, right? Talking about stability. So I'll just do straightforward stuff. So you have lambda 1 is less than 0. Lambda 2 is also less than 0. That means we have stable node. Okay, we have a stable node. All right. And that implies that we have stability. Okay, so we have stability. So that means that you have a point and everything, it's more like a sink. Everything converges to that point. So that's what that is about. Then what if we have lambda 1 is greater than 0 and lambda 2 is greater than 0? So we have an unstable node, and that talks about instability, right? Instability. And what do we do here? So we have a point that everything is going out of. So it's like a source. Things are getting out of that. Everything is moving away from that point. So we have instability. Then of course we have the possibility of having, say, lambda 1 is less than 0 and lambda 2 is greater than 0, or lambda 1 is greater than 0 and or and lambda 2 is less than 0. So if you have this kind of situation, we have a saddle. Okay, we have a saddle which implies instability. So it implies instability, meaning that if you have a point here, so every line coming gets diverted. Okay, every line coming gets diverted. So it's like something is coming, but then when it nears the place, it just gets diverted away from that point like this. So in this case now we have a saddle. So that's what we have, we call a saddle. On the other hand, we can actually have complex numbers, right? So if you have imaginary complex numbers, so we have if you just have the real part of an imaginary complex number, okay? An imaginary eigenvalue. So if that real part is less than zero, you know what we have? We have what we call a we have let me see. I know it is a sink, right? Yeah, we have a spiral sink and it is stable. Yeah, it is a spiral sink and it is stable. So spiral sink, and that implies stability. So what can you conceive the idea of a spiral sink? You have this sink now. You have this point, right? And then um something is coming from outside and going towards it. That's a spiral sink. So it's going inwards like this. So it's it's sinking into that point. So that's still convergence in a manner of speaking. Then what if you have the real number part of a complex eigenvalue to be greater than zero? You have what you call a spiral source. You have a spiral source, and that means instability. That is instability. So that's the spiral source. So imagine the source now. In this case now, uh oh, this is a spiral thing, spiral source. So this one now you have the spiral growing out of the source. It's going outwards. Okay. So that's instability. You have you have it growing out of the place. So of course another thing you can have is all you have is just you just have plus or minus whatever the eigenvalue is. Okay. Um, uh, so if it's all complex, if it's all complex, do I even need to put this now? Okay. So if it's all complex like this, so it means you have a cycle. Is it a set? I think it's a cycle. What it's a limit cycle, or you call it a center, and then you cannot conclude on the stability. Okay, so that's a center or limit cycle. So you have a center. Okay, I guess I need to change this. So here now, how do we do that? You don't have any real part, pure imaginary, right? Pure imaginary. So you just have just I lambda like that, only that. Okay. Um, Maybe another way to do this is if you can express it as a plus ib, that means this a now is less than zero, then this is a plus ib. Okay, so here it means all you just have for the eigenvalue is ib. That's pure imaginary, right? In that case, so that means you have a center, and what a center means is this: you have this point, and then the solution is just it's like an orbit around the center. That's why I think it's called limit cycle in some situation, in some manner of speaking. Okay, let's have an example here now. You have x dot equals x minus y, and y dot is x plus y. So the Jacobian, this is still looking like a linear system. This is still a linear system technically. So the Jacobian is straightforward. You just take the coefficients of the values. That's 1 minus 1, 1, 1. Or if you differentiate to, as we said, you still get the same thing. So if you so the eigenvalues here, you have 1 minus 1, 1, 1, right? If you remember how to compute eigenvalues, okay? So you have 1 minus 1, 1, 1. So you have the Jacobian is 1 minus 1, 1, 1. So we need to find the eigenvalues. So in that case, now we have for the eigenvalues, right? We need to find eigenvalues, eigenvalues. Okay, to find eigenvalues, we have like what's that thing now? Lambda I. So we have we have j rather minus lambda I, yeah, j minus lambda I equals 0. The determinant of that, by the way, so that means we have the determinant of 1 minus 1 1 1 minus this is a 2 by 2 matrix. We have lambda into 1 0 0 1, okay, equals 0. So here now we have 1 minus 1 1 1 minus lambda 0 0 lambda equals 0, like this. So we do 1 minus lambda here, minus 1 minus 0, that's minus 1. 1 minus 0 is 1, right? Then 1 minus lambda again, this equals 0. So and then we can take we can multiply that. We have 1 minus lambda into 1 minus lambda, then minus 1 times minus 1 equals 0. So you can tidy this up. This is simply 1 minus lambda squared plus 1 equals 0. So this is 1 minus lambda. If you expand this now, you have 1 minus 2 lambda plus lambda squared plus 1 equals 0. So in all, we have lambda squared minus 2 lambda plus 2 equals 0. If we use the uh, what is that thing called now? The quadratic formula. We know that lambda is equal to plus or minus. So here now, um, this is analogous to say a lambda squared plus b lambda plus c equals 0. Okay, so if we use this idea, we know that lambda is equal to plus or minus a minus b rather, plus or minus square root of b squared minus 4ac all over 2a. That's looking up for the Jacobian now. So lambda, okay, we are going to get to here. So we have lambda 1, lambda 2. So lambda 1, lambda 2 is equal to minus b. So our b here is minus, b is 2. So that's minus minus 2 plus or minus square root of b squared. That's minus 2 squared minus 4 into 1. That's a. And c is 2, like this, all over 2 times a, which is 2 times 1 again. So lambda 1, lambda 2 is equal to 2 plus or minus square root of 4 minus 4 times 2, that's 8, right? Yeah, all over 2. And then this is lambda 1, comma 2 is 2 plus or minus square root of, that's square root of 4 minus 8, that's square root of minus 4 all over 2. So square root of minus 4, of course, is, we have 2 now plus, square root of minus 4 is plus or minus 2i divided by 2. So we can divide through by 2. So we have lambda 1 comma 2 is equal to 1 plus or minus I. So that's what we get. In essence, we are saying that this is the same thing as having lambda 1 to be 1 minus lambda, if you like, and then lambda 2 is equal to 1 plus 1 minus I rather, and lambda 2 is 1 plus I. That's what this simply means. That's how you have this, the eigenvalues here. So, and because of the way it is, right, the real part, it is a complex number taken, and the real part is this one. The real part is greater than 0. So it is going to be a spiral source. So it means that we have an unstable system right here. So we can actually do the eigenvalues. All that long thing I did now, with this simple line of maths, you can just do, it is still linked to SymPy that we declared before now. So if you did not run that, this may not work. But because we already had that run, so we just say A is SP dot matrix. We have 1 minus 1, 1, 1. And then A dot eigenvalues. So we compute the eigenvalues. And then you just have 1 minus I. This I now is like the complex I, and with multiplicity of 1, and 1 plus I, another multiplicity of 1. So same thing I got solving, and that's what exactly you see here. So it means that with Python, you can actually get some of these things done. Okay, let me use this idea now to get to get another, I'll just impute another kind of matrix. Maybe I make a 3 by 3 matrix. So let's say this is now 1 minus 1, 1 minus 1, 1, 1, 1, 1, 1, 2. Okay. Then I now have this now, comma this. Then I have this, and I have, say, I have 2, 0, minus 2. Okay. Then I want the eigenvalues of this. Okay. It gets really complicated, gets seriously complicated like this. So we have, yeah. So it's so seriously complicated, but it's okay. just for the, I mean, we have some complex things right there, but it's okay. Now, let's go on to talk about the Hartman-Grobman theorem. This is a very important theorem when it comes to nonlinear analysis. So for the Hartman-Grobman theorem, can we fit all this together at once? Okay. Yeah. For the Hartman-Grobman theorem, if an equilibrium is hyperbolic, then we say that the nonlinear system is locally topologically equivalent to its linearization. And then near the equilibrium, the phase portraits are qualitatively the same. So that's the Hartman-Grobman theorem. So let me look for a simple way to describe this Hartman-Grobman theorem, right? Hartman-Grobman theorem. Hartman, Grobman. Yeah, right here. Okay, I want I like the AI version. So the Hartman-Grobman theorem states that near hyperbolic equilibrium points, a non-linear dynamical system is topologically conjugate to its linearization. This means the system's local behavior, such as trajectories, move toward or away from an equilibrium, is qualitatively identical to the simpler linearized model. So the linearized model, as we see in the Jacobian matrix. So whatever we have there, that's what. Okay, let me say in layman language now. In layman language, okay. So in layman language, we say that the Hartman-Grobman theorem states that near a nice or a hyperbolic resting point, a complicated nonlinear system behaves almost exactly like a simplified linear version of itself. So it allows scientists to ignore complex nonlinear curves. So the Hartman-Grobman theorem uh, seems to be giving us an easy way out for thinking about nonlinear systems, which can be quite complicated. Because in a complex system, small changes can cause unpredictable, non-proportional results like curved, tangled, or twisted behaviors. But linearization is a simplified, flattened version of the system, focusing only on the immediate neighborhood of a point, representing it with straight lines. And then when we talk about hyperbolic equilibrium, it is a resting point where the system is not perfectly balanced on a knife edge. That is, the linear approximation doesn't have eigenvalues to a real part of zero. Okay, that's hyperbolic. Then topological conjugacy. This is a fancy term meaning that if you look at the flow of the system, how points move over time, the nonlinear and linear models look qualitatively identical. They twist, bend, and move in the same way, even if the speeds differ. So this is a kind of justification for linearizing nonlinear systems. So it means that when you linearize a nonlinear system, the result you get from it is not too far from what you get normally, even if you don't linearize. Okay. Now, let's talk about, in talking about this, the idea of hyperbolic equilibrium came up. So we say that an equilibrium is hyperbolic if if the real part of lambda I, that is of a complex uh, eigenvalue, is not equal to zero. So if the complex part is not zero, if the real part is not zero, right? But if the real part is zero, we have a center. So it means that for hyperbolic equilibrium, you have a nice equilibrium point that you can really talk about. But if the real part were to be zero, we have a center and the stability cannot be it's inconclusive. So an equilibrium is hyperbolic if the real part of a complex eigenvalue is not equal to zero for all eigenvalues. So every eigenvalue goes like that. So if you have one eigenvalue where the real part is zero, then it is no longer the equilibrium is not hyperbolic, right? So hyperbolic types can be sink, where the real part is less than zero, that is stable. Source, where the real part is greater than zero, that is unstable. And it can be a saddle where you have mixed signals, which is still unstable. And linearization is valid for hyperbolic points. So if for equilibrium points that are hyperbolic, that are decisive, you can clearly say this is stable or this is not stable, then linearization is valid for such points. Okay. Then we talk about a saddle. We have a saddle example. Imagine this, that you have x dot equals x, y dot equals minus y. This is a hyperbolic saddle because the eigenvalues are 1 and minus 1. How do you know the eigenvalues are 1 and minus 1? Well, maybe it's not, we can read it off from this system. But if you want more clarity, you can just do the normal thing. X dot is x, y dot is minus y. Okay, x dot is x, y dot is minus y. So we have x dot that is equal to x, y dot is equal to minus y. So this is the same thing as x plus 0y, and this is the same thing as um 0x minus y. And if you want to do the Jacobian, what do you do? A j of x comma y is equal to differentiate x with respect to x, you get one. Differentiate uh, differentiate this expression with respect to x, you get one. Differentiate with respect to y, you get zero. Differentiate this with respect to x, you get zero. Differentiate this with respect to minus or with respect to with the whole thing with respect to y, you get minus one. So from here now, when you have when you have a diagonal matrix like this, or even a triangular matrix, that is a triangular matrix, you only have numbers along the principal diagonal and everything below it or above it is zero, then you can read off the eigenvalue straight. Here, lambda 1 and lambda 2 are simply 1 and minus 1. That's all. Okay, and this is a saddle because this one, 1 is greater than 0 and minus 1 is less than 0. So that represents a saddle like that. So this implies that you have a saddle. So that kind of point that everything is moving away from. So you have this point now. Things are coming and going away. Sorry, things are coming and they are moving out, coming, moving out, coming, moving away, coming, moving away. So you have a saddle like that. Okay, so that's the kind of thing. So this is a hyperbolic saddle. Hyperbolic because we have this one and minus one are real, right? They are non-zero rather. And that's why it's hyperbolic saddle because they have opposing signs. So we can represent that using Python code as you can see right here. So we have x, y is x, and then we return x and minus y, and then we have we are moving checking it over 0 to 5 and all that. So we just do this and we see what the saddle point looks like. Yeah, so you see the kind of thing I demonstrated that. So everything comes like it's coming towards that point, but then you have I kind of should I say asymptotic behavior? I don't know if that's the right word to use. Like it's coming there, but it's never getting there. So every line coming just comes and then it's diverted away from the point because there's confusion like that. You don't know what really to do when you want to go there, but you can't get there. Something like that. That's the idea of a saddle when it comes to stability. And then we have non-hyperbolic fixed points. In this case now, we say that, okay, I can expand this here we say that an equilibrium is non-hyperbolic. We already know hyperbolic, right? But an equilibrium is non-hyperbolic if there exists lambda with real number part of lambda being equal to 0. So in that case now, you have one of the eigenvalues tells you you have a cycle around that point. So you cannot really say yes or no about stability or instability. It is inconclusive. So you have examples when lambda is 0, if you have eigenvalue of 0 or you have eigenvalue of plus or minus I, and you don't have any number coming before plus or minus I. So in this case, the linearization is inconclusive, and the equilibrium are said to be non-hyperbolic like that. So you cannot determine the nature of the stability of the of one, at least one of the eigenvalues, right? So example is this: you have the center, so where you have x, you have a center here where you have x dot equals minus y minus x into x squared plus y squared, x minus y equals x squared plus y squared. So for the linear part now, you have minus y here. You have so x dot is minus y, and then y dot is x. So if you take away the linear part and remove the nonlinear part, so you see here that the eigenvalues are, you know, so for this part now, you have 0 for this first one. The eigenvalue is 0. And well, if you first take the eigenvalues, right? So you have 0 minus 1 and then 1, 0. So if you take the eigenvalue, this is the kind of thing you get. Okay, let me not be lazy. Let me just go. The idea of linearization is you don't care about the nonlinear parts. So you just use the linearization to be generalized. So you have x dot equals minus y and y dot is x. Okay, x dot equals minus y and y dot is x. X dot equals minus y and y dot is equal to x. Like I did before, this is 0x minus y, and here this is x plus 0y, like this, so that the Jacobian of xy would just be 0 minus 1, 1, 0, yeah? So how do you then find the determinant? So again, you have that's j, right? So you have the determinant, the eigenvalues. So you have j minus lambda I equals 0 for like that. So we have so j now is 0 minus 1, 1, 0 minus lambda, that's lambda 0, 0, lambda. Okay, and that is equal to 0. So you have 0 minus lambda, that's simply minus lambda, and then this is minus 1, and down here we have 1, and this is minus lambda again, and that is equal to 0. So here now, if you multiply this, you have minus lambda squared, that's minus lambda into minus lambda, then minus 1 into minus 1 equals 0. So we have lambda squared plus 1 equals 0. So lambda squared is equal to minus 1. So lambda alone is plus or minus I, because this is, okay, or if I don't need to skip. So lambda is plus or minus square root of minus 1, and minus 1 is I. So lambda is plus or minus I. So here now, this is non-hyperbolic, because you cannot really be conclusive about the nature of the stability here, because the real part of lambda is equal to 0. So it has no real part. So nothing comes. So if there was a real part, it would have been like maybe any number, say a plus b I, right? So this is the real part. So this real part a now is equal to 0. So you can't, you can't work with that. It's non-hyperbolic like that. All right. So in that case, you have nonlinear terms determining the stability. Nonlinear terms determine stability in this case, and this is what Hartman, Grobman tells us to. Okay, here you have equilibrium x equals 0. So for x dot equals x squared, I mean just equate x squared to 0, and you get just x equals 0. So linearization gives 0, but nonlinear behavior still dominates like that. So in this case now, we can try this out. You want to plot x by x squared and all that. So if you run this now, you get, the x squared still has the nonlinear behavior, right? But the equilibrium point is 0, as you can see right here. Okay. So now what happens beyond linearization? So what if you cannot linearize in the case of non-hyperbolic equilibrium points? So for non-hyperbolic points, we use center manifold theory, or we use normal forms, or we use Lyapunov functions, and even bifurcation theory. So let's see what we have ahead. For instance, let's talk about local invariant manifolds, right? We talk about center manifold theory. So let's look at local invariant manifolds. Can everything fit in at once? Okay, I think it can. All right. So local invariant manifolds. Consider that you have x dot equals ax plus f of x. So eigenvalues split into the following. It's stable when the real number part of the eigenvalue is 0. Unstable if the real number part of the eigenvalue is it's less than 0 here. Unstable if it is greater than 0. And then center if the real number part of the eigenvalue is equal to 0. Then there exist local invariant manifolds in that case. So what are the types of manifolds? You have stable manifold, which is W raised power S. Here you have trajectories approaching equilibrium as t tends to infinity. Then you have unstable manifold, WU, where trajectories approach equilibrium as t tends to minus infinity. Okay? Then center manifold, W raised power C, this contains neutral dynamics, right? So this seems analogous with stable, unstable, and center that we talked about there. So let's look at this. You have this example, x dot is x, y dot is minus y. So we have stable manifold here. Of course, the eigenvalues here are 1 and minus 1. So here we have the y-axis gives a stable manifold because the eigenvalue associated with that is minus 1. But the x-axis has an unstable manifold because the eigenvalue associated with it is 1, which is greater than 0. Okay, so we can demonstrate this using Python as usual. So here, if you have this Python code, yeah. So here you have x and NP0 is like x like that. So unstable manifold for x-axis and stable manifold for the y-axis in that case. So I'll just go ahead and run this. So and see this is exactly what you have. So you have for the x-axis, you have unstable manifold, x-axis, you have unstable manifold, and for y-axis, you have this okay. Yeah, x-axis unstable manifold, y-axis, you have a stable manifold right there. Okay. In summary, we have all this. We have for workflow, we find the equilibria, we compute the Jacobian, we find the eigenvalues and we classify stability. That's how we go. And then, so whenever you have a system, you find the equilibria, then you linearize and evaluate the equilibria in the Jacobian, find the eigenvalues from there and classify stability. So we have cases like hyperbolic. For hyperbolic, we can have linearization, to get the stability. And for non-hyperbolic, we can use nonlinear theory like manifolds and all that. And so the main tools we have here are things like linearization using Jacobian, and then we have Hartman Grobman, which tells us that every linearization you do is an approximation of a complex system as far as there are hyperbolic equilibrium points, right? And then we also have invariant manifolds, which is used to take care of systems that have non-hyperbolic equilibrium points. So we have some practice problems that you want to try your hands on. So instructions for each problem: find equilibria, compute Jacobians, find eigenvalues, classify stability, justify your conclusion, and use analytical calculations and Python where appropriate. Okay, so you can take some of the codes I have there and try to modify them to see how well they can fit into what you want to do, into each question, I mean. So here now we have find the equilibrium, find all equilibrium points of this, classify their stability. Of course, you have x equals 0 and x is equal to 2. Those are the two equilibrium points. So you have 0 and 2, right? So 0, you can't classify that. 2, that's instability. So that goes. So Jacobian and classification. So here you have a Jacobian matrix with 1, 1 minus 1, 1. So you can find the equilibrium, compute the Jacobian, find eigenvalues, and classify the equilibrium. Then for 3 and 4 now, so you have a nonlinear system where you have x minus y, then x dot y dot is y. So determine whether linearization is sufficient. Okay, you want to check that out. Linearization is only sufficient if the equilibrium points are if they are non hyperbolic, right? If they are hyperbolic rather. So and I can see already to find the equilibrium here, if you equate, you have x minus y squared, y and y, x minus y squared is 0, y is 0. So this y is 0 already tells us that this we have one non-hyperbolic equilibrium point, which is 0. And then if you put the 0 here, you also get x to be 0. So the linearization is not sufficient, so you may need to use something more than linearization in that situation. Then you have saddle point. Okay, study the system. X dot is 2x, y dot is minus 3. Of course, we can see that here that the Jacobian is going to be 2, 0 minus 0 minus 3. So the equilibrium points are 2 and minus 3. So the eigenvalues are simply 2 and minus 3. I mean, eigenvalues, I mean, are 2 and minus 3. Identify stable and unstable manifolds. The stable manifold is the y-axis. The unstable manifold is the x-axis, basically. Then for 5 and 6 now, center of spiral. Okay, if you use the so you want if you linearize the origin, that is, you can forget about the complex part, the complicated part. Just say x dot is minus y, y dot is x. So here now you have 0 minus 1 and 1, 0. So you can do linearize at the origin, classify the equilibrium, and determine whether it is stable. We did something like that before. Then for 0 even eigenvalue, x cube is 0, so everything is 0. Find the equilibria. The equilibria is you have zeros with a multiplicity of 3. Study stability. I mean, the stability cannot be concluded because, I mean, the equilibrium point is non-hyperbolic. Explain why linearization fails. That's the reason I just said that. Okay, 7 and 8 now. So find all equilibria, compute the Jacobian at each, classify each equilibrium. Of course, so to find all equilibria, equate both to 0. So I can already see x is 0, y is 0, and then you can solve the other system inside. And you're going to get like, I think you should be getting like 4 or so equilibrium points, and then you compute the Jacobian and all of that. Then you have the Hartman-Grobman application. Consider this, find equilibria, determine if they are hyperbolic, state whether Hartman-Grobman applies. So this shows you that if linearization is a very good approximation for a system as far as so if you can find any equilibrium pointer that is 0 or that is just purely complex, then that Hartman-Grobman cannot apply in that case. So finally, we have these two last ones. X dot is minus x, y dot is y. So we have minus 1 and 1. Find eigenvalues, of course, that, like I said, minus 1 and 1. So identify WS and WU. W stable, that's the minus 1. WU is for the along the 1 part. Sketch the face portrait. Of course, you have a saddle, so everything is going to be moving away from the equilibrium point. So central manifold preview. So we have x dot is y dot is minus x plus x squared. Find the equilibrium, compute the Jacobian, show that it's non-hyperbolic. Explain why a central manifold is needed. Of course, if it's non-hyperbolic, a central manifold will be needed. So thank you so much for this, for listening to this so far. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Try your hands on the problems and see how well you understand them. Um, if you have subscribed already, I thank you very much for that. If you haven't subscribed, I wonder why. So why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, and that comes with some special privileges. You'll find them when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.